Welcome to This Explainer. We are diving into an absolute game changer in manufacturing today. If you follow additive manufacturing, you know we've spent decades perfecting the art of curing liquid resins into highly precise structures. But what happens when you take that fundamental process and completely remove the liquid? We're going to explore the transition from traditional, fluid-dependent 3D printing to futuristic, solid-state UV cross-linking, a concept that was first proposed back in 2020. It's a massive shift that is literally untethering manufacturing from the constraints of gravity and stability. So I want you to start by thinking about this really fundamental physical problem. How do you 3D print in zero gravity when your ink is literally a liquid? Or, say, on a naval ship crashing through ocean waves? The reality is our current, highly advanced stereolithography systems are fundamentally earthbound. They absolutely rely on gravity to keep that liquid resin flat, stable, and perfectly still in a vat. The second you introduce extreme motion, the entire process breaks down. Okay, let's dive into this roadmap. First, we'll hit the liquid resin problem, then introduce a solid-state solution and the incredible materials making it happen. From there, we'll check out the 2D pipeline system, explore shape memory recovery, and wrap up with some exciting future applications. Section 1, the liquid resin problem, and exactly why earthbound tech fails in motion. When we look at standard vat photopolymerization, like SLA or DLP printing, the whole system relies on fluid dynamics playing nicely. The resin needs to level out, it has to be totally free of surface turbulence, vibrations, and sloshing. But contrast that with the environments where we actually desperately need on-demand manufacturing. Think spacecraft in microgravity or maritime vessels dealing with random, severe vibrations. In those scenarios, your liquid resin is flying everywhere. It splashes, it shifts, and your print precision is just completely ruined. Section 2, a solid-state solution, decoupling curing from fluid dynamics. So the crucial question is, how do we fix this? Well, the brilliant aha moment was realizing that to solve the liquid problem, you just get rid of the liquid during the printing phase, period. Prior to 2020, liquid printing completely dominated high-resolution additive manufacturing. But then, the concept of solid-state UV cross-linking for volumetric additive manufacturing was first proposed in 2020. And man, it has accelerated incredibly fast since then, moving from theoretical chemistry straight to working pipelined 2D prototypes. Instead of a vat of liquid, the process starts with a pre-stabilized solid block of material, a precursor that already holds its own shape. Then, targeted UV light is used to cure and cross-link the specific pattern directly inside that solid block. Because it's already a solid, you don't have to worry about materials sloshing around. Once the curing is done, the surrounding uncross-linked material is simply washed or melted away, leaving a perfect part. Section 3. The materials making it happen, from thermal gels to vitrimers. Now, obviously, to print on a solid, you need some very special chemistry. You can't just shine UV light on a random block of plastic and expect a part to magically appear. Enter materials like thermal gels and vitrimers. Think of a vitrimer like a material with a reversible lock. At low temperatures, it's locked into a strong, stable solid. But if you heat it up, those bonds temporarily unlock, allowing it to flow, kind of like a thermoplastic. So we prep the material to be physically solid at room temperature, but chemically it's just sitting there waiting to be permanently locked by that UV light. And this brilliantly illustrates the sheer mechanical strength of these precursor materials. Even before printing, an uncross-linked thermal gel is solid enough to easily bear the weight of a heavy stack of coins without collapsing or splashing. Once UV light is applied to cure specific geometries inside the gel, the uncross-linked support material is removed, leaving behind highly durable, elastic shapes, like crosses and cylinders, that are fully finalized. Section 4. The 2D pipeline system, automating the solid-state process. To take this out of the chemistry lab and into the real world, researchers at Nanyang Technological University designed a pretty amazing automated 2D pipeline system. The workflow is incredibly clean. First, resin pretreatment, where the material is prepared as a flat, solid sheet. Second, loading that resin and an optical mask onto a moving platform. Third, a precisely timed 25-second UV exposure. And fourth, sample separation, where the uncured material is washed away. There's no messy recoating cycle, no waiting around for liquid to level out. The platform just steps, exposes, and moves on. Of course, getting the system to work perfectly required locking down the exact optical physics. Through a ton of testing, they found the absolute optimal parameters to balance curing completeness and dimensional accuracy. The ideal distance from the UV source to the mask? Exactly 13 centimeters. The gap between the mask and the solid resin? Just 5 millimeters. And the optimal exposure time is exactly 25 seconds. So why do those specific distances matter so much? Well, light follows the inverse square law and spreads out at the edges of a mask. If your UV light is too far away, it loses intensity. If the mask is too high above the resin, the light diffuses and spreads before hitting the surface, which totally blurs the edges of your printed part. But by holding strictly to this 13 centimeter and 5 millimeter geometry, the UV light remains perfectly constrained, giving you incredibly sharp edges.
Section 5. Shape, Memory, and Recovery. Self-repairing structures.
Now, there is a bit of a catch to printing inside a solid block. When you go to mechanically peel or wash away that uncross-linked solid material at the very end, you have to apply physical force. And that force can warp or crush the delicate part you just made. That's exactly why the chemistry we discussed earlier is so crucial. These printed hydrogels and vitrimers have something called the shape memory effect. They basically remember the geometry they were printed in, and they automatically return to their original shape when triggered by something like cooling or water.
Now, what's really interesting here is just how fast this self-repair actually happens. If a printed bone-shaped hydrogel gets severely warped and compressed, say from the damage of tearing it out of that solid precursor block, it isn't ruined. Give it the proper stimulus, and it physically unfolds, perfectly recovering its programmed shape in a matter of seconds. It's essentially a self-repairing mechanism built right into the manufacturing process.
Section 6. Exciting future applications. Bringing 3D printing to the extremes.
By combining this solid-state UV cross-linking with the shape memory effect, we are unlocking manufacturing environments that were completely impossible even 5 years ago. Just imagine an astronaut on a space station safely printing a replacement gear from a solid block of polymer, completely without the worry of liquid resin droplets floating into the cabin. Think about a turbulent naval ship printing emergency repairs on the open ocean, totally immune to engine vibrations. This is a real game changer for moving aircraft, vehicles, and even printing advanced biomedical implants, where messy liquid processes are a massive liability. And this brings us to a truly fascinating frontier. We have successfully decoupled high-precision manufacturing from the need for a perfectly still, gravity-bound room. So the question I want to leave you with today is this. As untethered, vibration-proof solid-state manufacturing continues to scale up, how is this going to completely reshape the future of human exploration? Thank you for hanging out with me for this explainer, and I hope this gave you a really clear window into the incredible future of additive manufacturing.